Hi class, welcome back to the next section, chapter 1.3, where we talk about diffQs as models, that model applications, right? So this is mathematical models using differential equations. So we're not going to formulate a lot of models, but we're going to review a lot of models. We'll talk about their components, about how they work, what they use to model, things like that, right? So this is more of like an overview. We have a couple of examples at the end where we're given a situation and then we create a model from scratch. Okay, so let's go ahead and get into this, right? Okay, so again, in this section, we're going to cover a brief overview of the basic models that we have for modeling diffQs for application problems. One of the big things to remember is that derivatives model a rate of change. So we use a diffQ whenever we have to model something changing. Okay, we stated a little bit earlier that if we have a function that represents position, the first derivative is velocity and the second derivative is acceleration. Then the derivatives after that represent other things, things like jerk, snap, crackle, and pop, right? Things that are typically not used unless you're engineering roller coasters and cars and things like that, right? So if we're talking about a system or we're trying to model something that has to do with movement, we generally will use things that have to do with position, velocity, and acceleration, right? So that can be a second order diffQ, because if we have acceleration in consideration, I'm going to need a second derivative somewhere, right? The derivatives also are used for related rates, right? A common one that you see in calculus is you're blowing up a balloon. How is the volume changing in relation to the surface area of the balloon as you blow it up, right? So the two rates are related because obviously as you put more gas into the balloon, its volume increases and so does the surface area of the balloon itself, right? So how do those two rates coincide with each other? It's used for optimization problems. The common thing that most students remember about derivatives is you use it to find critical points, and then you can use those critical points to find the global max and mins and the local max and mins of a polynomial or some other sort of curve. So optimization always has some sort of derivatives in there. You can use derivatives to find curvature, right? Mostly concavity, right? When am I concave up, concave down? You need a second derivative test for that. So that's the use of derivatives in optimization problems and linear approximations, right? So maybe the function I'm trying to model is extremely difficult and I can use its derivative instead. We're going to actually see quite a bit of linear approximations come into play in section 2.6 actually. Okay, so the construction of a math model starts with figuring out what the variables are, right? What are the things that are changing, because that's what derivatives model, right? Rates of change. So what are the things that are changing? Those are the things that we probably need to have a derivative for, right? In terms of for that function, right? In my diffQ. So I need to figure out what the variables are, the things that change, and then how do those functions relate to whatever else is going on in my system. However, if you think about a system or something that you want to model, you can easily get down this rabbit hole of, well, this thing changes and this thing changes and this thing changes. We generally don't need to talk about all the things that change, right? So for instance, if I'm throwing a ball, right, a very, very simple model for all you physics students, math students even, right? Projectile motion is something that we study since Algebra 1, pretty much. So when I throw a ball, I'm changing height, I'm changing distance, right? So there's a change in X and Y. There's a change over time. I can model lots of different things. I don't need to take all of those things into consideration though, right? I can really kind of focus on one and just say, hey, my independent variable is X, let's focus on that, right? Or my independent variable is T, and let's focus on that. I don't need to talk about position and time together. I can, but a lot of times that's unnecessary unless I want to make like a parametric equation or something, right? So keeping a equation or a system simple with a general model will be useful, and then I can adjust it to be as more and more difficult as time goes on, right? So for example, for projectile motion, if I'm talking about throwing a ball, I don't have to take air resistance into a chord, right? I generally don't have to talk too much about gravity, right? I mean, I do, but I don't, right? Like, it is there as the first term, obviously, when you make a quadratic form, but I don't have to take the motion of the earth into consideration, right? I don't have to talk about the wind. I don't have, like, there's certain factors that don't come into play unless I want to make a very, very detailed model. Now, if I'm talking about projectile motion, where I'm like a sniper in the army and I have to shoot a small target a mile away, now I have to deal with the motion of the earth. I have to deal with wind. I have to deal with air resistance. So I'd use a more detailed model at that point, because those do come into play for that situation. Whereas throwing a ball to my friend, I don't, right? So we call this specifying the level of resolution. So you'll hear me say this in later videos where, oh, we want a more resolute model, or we don't need a high level of resolution here. We can use this basic model. So as we go through this course, right, through this video series, we will have videos that are, well, we will have models that are very, very basic, very standard. They might not seem like it at first because you're like, oh, this thing is crazy, right? But as we go through the sections, those same problems will come up again and again and again, and we will start to add layers to them, making them more accurate, more representative of different situations, but it'll be the exact same model. So I believe we have about 3 or 4 different modeling sections. This is the intro modeling section of the textbook, and this is where we kind of just say, hey, here's all of the different equations that we have, and then as we go down the line, we will start introducing more and more accurate layers into that model to take into consideration different outlying factors. Okay, so we should next make a set of reasonable assumptions about the system that we're trying to describe. Okay, so this is where we are sort of going over our model, and we're trying to adjust it to make it more resolute if necessary, right? So these assumptions will include any calculations derived from formulas that may be applicable to the system. So for instance, if I'm going to talk about shooting a rocket into space, I can come up with some sort of differential equation that maybe it's another quadratic, right? But then I just stop the time. I make it with consideration over time, and I stop the time at the vertex of the function, where the vertex of the function coincides with the outer atmosphere of the Earth, right? Because then that's when the rocket is no longer in orbit, right? Or it goes into orbit, right? And then when I come back, I say, well, that's a very basic model. I'm not really taking into consideration things like the change in weight over time as I dump my fuel, as I burn my fuel, right? Maybe I need to come back and add in things like air resistance, right? So then I come back and I make assumptions and calculations that are derived from applications of the system I'm trying to model, and then I start to add those in. So it's a circular process where I kind of make a basic model, I make some assumptions, I see if they work or not, and then I add those into my equation, and then I see if it works, I make some assumptions. So it's a sort of a circular process, right? So again, that's adding varying levels of resolution, right? So like I said, we're going to visit several problems over and over again, where we go into greater and greater detail and analysis, right? So this is the model that we have for this, okay? We kind of start here with some assumptions, and then we want to express these assumptions in terms of a diff EQ, right? What are my variables? Let me try to make some sort of what's changing over time, and then turn that into some sort of a mathematical formula. I want to solve my differential equation, obtain a solution, and then I want to see if my solutions accurately predict what is actually going on, right? So I'm going to check my model with known facts that actually happen, right? If it's accurate enough, I can keep it for what I need. If not, then I need to make some assumptions and increase the resolution, right? So I can go through this process over and over again where I am now trying to add in layers of resolution as necessary until my model is good enough or even better than I need if necessary, right? So let's go over some of the basic models. So in this section, we're just really reviewing an overview of the models. And then at the end of the textbook section of 1.3, there's a section where it just says, hey, here are some other models, right, where we don't have the formulas for you, and we want you to go over the formulas and make them yourselves. And so we're going to take a couple of those questions, and those are the example problems in the back, right? So the majority of the problems in this section, we're going to go over right now the formulas for and how they work. And at the end, I kind of took some of the harder problems from the homework section here to create some models for us. Okay. So our first model is going to be population growth, right? So you've talked about population growth since Algebra 2. It comes up in pre-calc, comes in Calc 1, and I think it also comes up in Calc 2 quite a bit. So we know that the rate of change of a function over time is equal to a constant multiple of that population, right? So again, K we call our constant of proportionality, right? So the rate of change of a population over time varies directly proportional to the population, but not equal to the population. It's some constant multiple of that. So that's our constant of proportionality, right? So you guys have seen this before. When we talk about masses on a spring, similar to Hooke's law, same thing, right? You have the constant proportionality. So that's how that works, right? So P of t is population at time t, right? So dp over dt is the derivative of this function, right? The derivative of your population with respect to time. K is positive, right? And it's a constant of proportionality. So this is for population growth, right? If K is negative, if your constant proportionality is negative, then you have decay. It's a decay model, so you have a decrease in population. So generally when we have a decrease, we'll use that for radioactive decay because it always decays, right? So here it's the same thing. A is my amount of a substance at time t, right? And K, the constant proportionality here, is going to be negative because my amount of a substance is decaying over time into other elements, right? Other atoms, other molecules, other compounds, whatever is happening with my radioactive decay. Generally, you're losing electrons at that point, right? Newton's law of cooling, okay? So our function for this is dt over dt is equal to K times T minus Tm. So here, T of T is my temperature at time T, right? So if I'm putting an object in the oven, my temperature of that object is T, and as time goes on, the temperature increases, right? Now, if I'm talking about cooling, if I take something out of the oven, it's at a higher temperature, and then as time goes on, it cools down towards the ambient temperature, Tm. Okay, so Tm is the ambient temperature, or the temperature of the surrounding medium. Now, I said medium because it's not always air, right? If I put an object into an ice bath, right, the surrounding medium is in the ice bath, right? So it's whatever the temperature of the medium your object is cooling in. Okay, again, K is that constant of proportionality. T minus Tm should be positive, right? If I'm cooling down, if this temperature is larger than the ambient temperature, that's what I'm cooling down to. That means this constant proportionality should be negative because I am decreasing a positive value, right? So Tm is a real number, right? It's a constant, and my constant proportionality is negative because I should have a decreasing function, and it should be decreasing to T of m as time goes to infinity, right? So now let's talk about spread of disease. Okay, so before we go into spread of disease, let's think about this before we just throw out the equation here. Okay, spread of disease is going to increase over time, right? So my derivative should be some function, right, that represents the amount of people diseased over time, right? So I should have the derivative of that with respect to time equal to some constant proportionality, some value k, that is positive, right? And I should probably have more than one variable here because I'm having interactions of people, right, who are infected with people who are not infected. Okay, so I need to have some sort of relationship there. K times, maybe it's x plus y, maybe it's x squared, x times y. Let's see here. It's actually x times y, right? So x times y is the number of interactions between people who are diseased and people who are not diseased. Okay, so x of t is the amount of diseased people at time t. Y of t is the amount of people that are not diseased at time of t. K here is going to be positive, and x times y is the number of interactions between the two groups. Okay. Chemical reactions, right? So for a chemical reaction here, we're going to start with a basic model, and this is one of the ones where we definitely start to add layers of resolution in the later sections, as well as the population model. Population growth also, that's a very common model to use, so we're going to add layers of resolution to that in later sections. So here we're going to start with a very basic reaction where we have a compound that starts to break down into something else. Okay, so first order reaction is a substance that's undergoing a chemical reaction, decomposition, and it's going to be modeled by the decay model, right? So again, this is very similar to radioactive decay. You just have some chemical that's decomposing over time. Okay, so it can be something volatile or something not too volatile. Maybe it's left out into the air and it's disseminating. It's just decaying over time based on time, right? So here we're using capital X. Capital X is the amount of your substance that is remaining at time t as it decomposes to smaller molecules. Okay, here K is negative because this is a decay. It's a decomposition that's going on, right? A second order reaction is where you have two different chemicals reacting together. Okay, so you have a substance A and a substance B combining to create a new substance, right? So here we have to talk about the amount of your substance C after time t that's being created by interactions between A and reactions of B. So here this is going to represent how much of A is left over at time t to interact with how much of B is left over at time t to create time your element C, right? Because the amount of elements that's there is going to dictate how fast that reaction is happening, right? If you only have a little bit of A and a little bit of B left over, there shouldn't be a lot of reaction going. However, if there's a lot of A and a lot of B left, they should be interacting because there's more substance to interact with, right? So again, X of t is the amount of our substance C that's created after time t during our chemical reaction. A alpha minus X is the amount of substance A remaining during this interaction at this specified time. So whatever has not been converted yet into our new substance. And beta minus X is the same thing. It's the amount of B that's left over at time t. Again, whatever is not converted into C yet, right? So here, first order reaction is a decay. It's a decomposition. Some complex molecule that's breaking down over time. And then here is probably what you're more familiar with when you think about chemical reactions, which is, the mad scientist in the lab mixing this with that to create something new, right? So here, you are mixing two substances to create a new substance. And here is just a substance that is, for lack of a better term, unstable and decomposing into other substances or losing electrons or what have you, right? So the first order is more like the radioactive decay, whereas here this is us combining two substances together, where the rate of change of creation of that new substance is a constant multiple that's proportional to the amount left over of one substance and the amount left over of the other substance that's being used for that mixture, for that combination. I don't want to say mixture because it's not always a mixture, right? Sometimes you have two dry solids together and you have to heat them, you know, things like that. So mixtures, okay? So this is actual mixtures. So mixtures, we will cover these quite often. I actually use these a lot. So when I say use these a lot, I mean like in problems in this course. So we will definitely be going over mixtures quite a bit. We will be adding layers to this as well. This is a common one that we will be increasing our level of resolution on. So make sure you get familiar with these because they will definitely show up. You will 100% see these on your exams and homeworks. So here we talk about the amount of a mixture at time t, okay, and that's going to be equal to the rate of input or inflow of your substance you're trying to mix, and you're going to subtract out the rate that your mixture is leaving. Okay, so let's think about like this. Really what's going on is, let's think about you have a tub of water, okay, and to this tub of water you have a pipe coming in that has pure brine coming in, right? Brine is what they're generally using, but some substance, okay? So it has 100% concentrate coming in and it's being mixed in a vat of water, okay? So for your initial value, you have absolutely none of your solution in your tub. It's nothing but water, right? So you turn on your power switch, you have a hose coming in, and it's coming in with 100% in solution and it's mixing in with something with 0% solution, right? And then maybe you have an outflow, and your outflow is your mixed solution coming out, right? So as you turn this on, obviously you'll come to some sort of equilibrium where you have a percent solution inside of your tub at all times, right? As time goes on, ideally that's what's happening. And so that's what we're trying to figure out, right? So again, this is a good problem for industry, right? If you're creating something, let's say something fun. Let's say you're making beer or something, right? So you have an inflow coming in, and it's being mixed with your hop solution as it's being brewed, and then you have an outflow coming out, right? So it'd be nice to be able to model this, right? So AFT is the amount of substance in a mixture at time t, okay? The derivative of A with respect to t is the net rate of substance in a mixture, okay? So the amount of substance in that mixture at time t. So the rate in is the concentration in your inflow times the input rate of mixture, okay? So how fast is it coming in, and what's the concentration in what's coming in, right? So that's going to be the input rate of your substance, right? Your rate out is the same thing. It's the concentration in the outflow. So how much is concentration wise? Is it like 10% in your solution that's coming out? And then how fast is that leaving your tub or your mixture, right? So that's going to be the output rate of your substance, right? Okay, so next let's talk about draining a tank. So let's say we have a really any size shape, cylindrical, conical, right? It doesn't really matter. But the volume of a tank changes over time, right? It's going to be equal to the negative area of the hole that it is being drained from, okay, times the square root of 2 times the gravitational constant times the height of our tank, right? So for this case, we're mainly talking about a cylindrical tank. Here, 2 times the gravitational constant times the height is the velocity with which the water drains, right? So here V of t is the volume of water in the tank at time t, and the velocity, the speed of water leaving the tank, is this constant here, which is 2 times the gravitational constant times the height of the tank that we are looking at, right? A sub h is the area of the hole the water is draining out of, right? If I divide this equation by AW, right, which is the surface area of the water on the top layer, surface area, then I get the rate of change of the height of the water over time instead of the volume over time, right? So here h of t is the height of the water at time t, and a sub w is the top surface area of the water. Okay. Series circuits. So series circuits, this is one that we will see quite often as well. Okay, for all of my electrical engineers in here, you generally do pretty well when these problems come up. So these again will start off basic, and then we'll add layers of complexity to them, right? So here we have a very basic LRC circuit. Okay, so it's in series, right? We're just going to talk about the components here, right? So as we go on through this course, we will start to add parallel series as well, and then we can talk about how those work. We'll take out the C and only have an LR circuit or an RC circuit or what have you. Okay, so we'll add varying levels of complexity here. So the current here, right, the current throughout the circuit is equal to the rate of change of the charge over time. Okay, so I of t is the current in the circuit at time t. Q of t is the charge on the capacitor at time t, right? So my voltage across the inductor is L, right? This is the resistor, this is the capacitor. Sorry if I forgot to say that. E of t is the voltage drop. This is where the start of my voltage comes in, right? So this is basically where the battery is, right? This is the power supply here, right? So the voltage across the inductor is L times the derivative of I, right? The rate of change of I. So the inductance times the rate of change of current over the inductor. So the derivative of I is the same as the second derivative of charge, right? Because I is the derivative of charge over time, so the derivative of I is the second derivative of charge. So we can rewrite this as L times the second derivative of charge over the capacitor. Okay, so the inductor, L is the inductance and is measured in henries, right? The voltage drop across is L times di, or L times the second derivative of Q, right? So the voltage drop just means how much voltage is going across this inductor, right? So the current goes over the inductor and it changes over the inductor, right? So the voltage across the resistor is I times R, and we know that I is the first derivative of Q, so we can write this as R dQ over dt, right? So the resistance is measured in ohms, right? And so the voltage drop across, so the change in voltage over the resistor is I times the resistance, right? And then we have the voltage across the capacitor. So that's 1 over the capacitance times the charge. Your capacitance is measured in farads, right? So your drop in voltage, the change in voltage as it goes over the capacitor, is 1 over the capacitance times the charge. Okay, so the impressed voltage, that is the voltage in the entire system. How much comes in is how much needs to come out, right? So to measure your impressed voltage, or really just the voltage of your system, you're just going to add your voltage change across all of your objects, right? So you just add all those pieces together. Your change in voltage over the inductor, your change in voltage over the capacitor, and your voltage drop across the capacitor. I think I said that wrong. So your inductor, your resistor, and your capacitor, you add those all together. Now, if I had more elements, let's say 2 resistors, I would add my 2 resistors together, right? So you're just adding everything together as it goes through the system. Okay. Falling bodies. Now, we didn't really talk about this, but I use this as an example, right? I use projectile motion as an example. But when you're talking about falling bodies, you have acceleration due to gravity. we do have to take air resistance into consideration here, right? So this is going to have a relationship between your mass, your acceleration, and the resistive force of air that you're falling through, right? So S of t is going to be the position of a falling object at time t, right? So where are you as time goes on? How close are you to the bottom? How fast are you going, right? So that's going to be the first derivative of your position function. And then how fast are you increasing your speed as you fall, right? So your acceleration due to gravity, which is your first derivative of velocity, which is your second derivative of your position, right? Because velocity is the first derivative of position, so acceleration is first derivative of velocity, so second derivative of position. Okay. You should be familiar with this. Force is equal to mass times acceleration. So we can make a substitution here. What is acceleration? It's the second derivative of your position, right? And we know that when we're falling, our acceleration is due to gravity, right? So this force equals ma is equal to negative mass times gravity. Now, why negative? Well, because you're falling downwards, right? So this has to be a negative value. So we can imply here that the second derivative of our position function is just equal to gravity, and we're moving downwards, so that's why we have the negative value here for gravity. Okay. Weight equals mass times gravity, right, is the weight of an object. Okay. So air resistance, right? So mass times, this is acceleration, right, is equal to your mass times acceleration times a constant multiple of your velocity. So this is where the air resistance comes into play, right? So viscous damping due to air resistance. So the rate in which you are falling is going to be retarded or decreased by your air resistance, right? So constant multiple of your velocity, the faster you go, right, the more that's going to change. Your air resistance is going to change. So m times g is the weight of the object, right? Because mg is weight. And so here, we're no longer calling mg negative, because for air resistance, we are calling the downwards position the positive direction. Okay. So when we're talking about falling bodies, we're going to use negative mg. When we're considering air resistance, the air resistance is moving up. So that's the resisting force. We're calling that negative. And the downward force due to gravity is the positive side. Okay. Suspended cables, right? So this is always fun for people. When I say that sarcastically. Nobody likes dealing with suspended cables. So let's say we have two cables being suspended. Okay. This is my wire, right? W is the total vertical load between points P1 and P2. Okay, so this downward force here, this weight, it's basically the weight of the wire, right? It's a force, right? It's a downward force. It's due to the weight of the wire. So we have it measured with a vector, right? Boldface here is for vectors, so W is a vector. T1 and T2 are also vectors. So this weight has a downward force, a downward vector representing that force due to its weight pulling down. Okay, so W is the total vertical load, or you would just say the downward force due to its weight, and that's between the points P1 and P2 here. Okay, so here P1 is the lowermost point, right? So if this was a quadratic, it would be at the vertex, right? So at the vertex point, it's the downward, it's the lowest most vertex, the minimum value, and P2 is just some other point along the curve, along the wire, right? T1 and T2 are tangent vectors. So T1 is the tangent vector to P1. Now I drew it in this direction. We could draw it in that direction too, really. And then T2 is also tangent, but at this point P2. Okay. The magnitude of T1, okay, is going to be the magnitude of T2 times cosine theta, right? So again, The magnitude, like I said, it doesn't matter the direction. It does and it doesn't, right? So the magnitude at this tangent point, if I were to switch directions and I just moved it in space, because that's what you can do, it would be equal to this tangent vector here when we do our right-hand triangle for our trig functions, right? And so it'd just be the length of t2 times cosine. Remember, cosine is when you have a radius of 1, so you have to multiply it times the amount you're extending it by, which is the magnitude of t2 here, right? So the magnitude of this t1 is the same as this magnitude here. It's really, if I just picked it up and I put it here and I change its direction. So if I want to find its length, I'd have to talk about it in terms of this other tangent vector I have here, right? The weight here, okay, is the same as this vector, right? So this vector is the same. I don't want to say it's the same. The magnitude of this vector is the same as the magnitude of this vector. Again, direction-wise, it's pointing in the opposite direction, right? But its length is the same as this length. So the amount of force that this represents is the same as the amount of force that this represents. It just happens to be that they're pointing in different directions. And that's just really, if I were to take this T1 and take this W and move them, change both of their directions and move them in space, right? In relationship to this T2, they would then be equal in this fashion, okay? So the tangent of theta here is going to be basically opposite over adjacent, right? And so my opposite is the magnitude of W. My adjacent is the magnitude of T1. So I just put those where they are, right? I can write them in terms of W1 and T1. And so we know that's really just a change of y over x. It's the first derivative of position. And so that is how we find tangent, right? So we have it now in its component terms. Okay, so let's do a couple of examples and then we'll be done with this section. So let's say that we have a person, which we'll call P, that's starting at the origin. So we're really, what we're doing is kind of drawing an axis just to help us with this problem. And so let's say that this person starts at what we'll call the origin of this system, right? He's going to move in the direction of the positive x-axis, right? You're going to be pulling a weight along a curve C where it is attached to a rope. The curve is going to be called the tractrix, right? As shown below, which will come up in a second. So the weight initially located on the y-axis at 0s, okay, is going to be pulled by a rope that has a constant length of s, right, which is kept taut throughout the motion. So we want to determine a differential equation for the path C of the motion. We're going to assume that the rope is always tangent to C. So here's our curve. So let's go over this one more time as we look at this picture. So let's think about this a little bit differently. Instead of looking at it as a graph with a curve and a line, okay, you're standing in your backyard or in your front yard or on the street or whatever, okay? You have a rope tied to a weight and you walk away from the weight until your rope is completely straight, completely taut, okay? From there, you turn 90 degrees and you just start walking and you drag this weight on the ground, okay? So the whole time the rope should be taut, it should never get slack, and you're going to end up dragging that weight along the ground, okay? And the curve in which that weight drags is this curve C. That's what a tractrix is, okay? And as you are pulling it, this is the length of your rope here, this length S. It never changes, it's always S. At this point it was S, and as you walk, this is S. So S is always tangent to this curve that your weight is flowing along the ground. Okay, so that's what's going on. Right, so sometimes you have to kind of step back and take this word problem and say, okay, if I were to do this, what would this look like, rather than top down looking at some graph, right? So that's kind of what's going on here. Okay, so the things that are constant here are S, right? There are a few things that are changing. The angle between the line that you're walking and the rope is going to change, and the distance between the line that you're walking and the weight to that line is also going to change, right? So we have two things that are changing here. We have Y is changing over time, theta is changing over time, and obviously X is changing over time over time as well. However, X is our input, so we're not going to differentiate X, but we'll differentiate in terms of X. We could differentiate in terms of theta, but that's a little bit harder to do as well, right? But always this output is Y, right? So what we're going to do here is, generally when I talk about this problem to students, they always want to do it in terms of theta. Now that's going to be hard to do because you can't really measure this angle theta as you walk. However, you can always measure this distance X as you walk. That's very easy. You can literally walk with a tape measure with you as you walk, but you can't walk with a protractor that is changing over time as you're walking between this angle. You know what I'm saying? Like, it's hard to do that. So when we make this model, we want to use the constant values that we have, right? And not these weird values that we're using, right? So we are, however, going to use theta in our derivation for what we want to use. So remember, S is always constant and Y depends on this value of S. So what we can do here is we want to use rate of change, right? This line is always tangent to C, so we have a triangle here, right? If I just find the tangent of this triangle, it's always equal to the derivative of this line, because your derivative is your rate of change, right? So the easiest thing to do is to just solve for this triangle, right? So that's what we're going to do here. So Y will decrease as P moves in the positive axis, right? Y is decreasing as you move. The line connected to P, from P to 0S, will always be tangent at this point XY. So the slope of my line is going to be tangent of theta minus pi minus theta, right? So if this whole thing is pi and this is theta, well then this part has to be pi minus what's been used up, right? So this is pi minus theta. But as I said before, theta is not very intuitive here, right? So theta changes as P moves in the positive direction. We would prefer to have an equation that uses our given values, right? We're already talking about position in terms of X and Y, so I'll know an X and I'll know a Y. Those will be kind of given to me as I move, right? Theta is not. So it's easier to use something that we have rather than create values and functions for things we don't have measures for it, right? So using the Pythagorean theorem to solve this triangle, we can find the distance from Y to P, okay? The distance from Y to P, okay? Actually, I think I wrote that wrong. The distance from X to P, I should say, right? This distance, okay? Y squared plus this distance squared, P minus X squared, is S squared, right? So if I want to find the distance from X to P, so I'm being really lazy right now. Normally I would just pause this video and fix this. But I'll fix this in the write-up. So this should be the distance from X to P is going to be the square root of S squared minus Y squared, right? So Y prime, right, the rate of change here is tangent of pi minus theta, which is just the same thing as that solved triangle. Here Y is decreasing, so we have to make this negative, right? So rate of change here is a negative value because it's a decreasing function. I'm decreasing over time. So I'm basically just solving this triangle and finding the tangent of this triangle in order to represent my rate of change. Okay. So next example. So in meteorology, the term virga refers to falling raindrops or ice particles that evaporate before they reach the ground. So we're going to assume that a typical raindrop is spherical, right? Starting at some time, which we can designate as T naught, the raindrop of radius R naught, right, so it's the initial radius, falls from rest from a cloud and begins to evaporate as it falls. Okay. A. If it is assumed that a raindrop evaporates in such a manner that its shape remains spherical, then it also makes sense to assume that the rate at which the raindrop evaporates, that is, the rate at which it loses mass, is proportional to its surface area. Okay. Show that the latter assumption implies that the rate at which the radius r of the raindrop decreases is a constant. Okay, so we are going to take the assumption that it loses mass proportional to its surface area, and then its rate of change decreases at a constant rate. Right? We're going to find r of t, the radius at time t. So we're saying that it's spherical. The volume of a sphere is this equation here. Okay. We know that surface area, right? We're talking about volume. We're talking about surface area. Surface area is the first derivative of volume, right? So we're saying that the volume changes over time and the radius changes over time. So we're going to take this derivative with respect to t. R here is a function of t. So when we take its derivative, we need to differentiate this implicitly, right? Since there are no t's in this equation, but there are functions of t's on both sides, we differentiate it implicitly, right? Mass is k times v, right? So this is a constant multiple of its volume, right? So if its volume is large, then its mass is large, right? If its volume is small, then its mass is going to be smaller. So some constant proportionality of its volume is going to be the mass, right? So we also said this here. If it assumed that a raindrop evaporates in a manner that it remains spherical, the rate at which it loses mass is proportional to the surface area. Its mass should be proportional to its volume inherently, right? Because it's a raindrop, right? So here I'm going to have mass is k times v, or k times v here is 4 pi r cubed, right? So that will be the mass. So it's a constant multiple of the volume. The first derivative of mass will be this function differentiated with respect to t, right? So I could have just taken this v prime and then thrown it into this equation, but here I threw it in first and then differentiated, so it doesn't really matter. But it's nice because when I differentiate this r cubed cancels with this 3, so we got the 4 pi, and then the r squared times r prime that's left over from the chain rule of differentiating implicitly, right? So my change now in mass, right? The change in mass is a constant multiple that's proportional to the surface area, because this now represents the surface area, right? And surface area is 4 pi r squared, so that means that k and r prime have to be a constant because it's a constant multiple of the surface area. So kr prime is a constant multiple of the surface area, 4 pi r squared, right? So let's give this a name, just to make it easier. We'll call it lambda, right? So m prime is lambda, this constant, times the surface area. Surface area is 4 pi r squared, right? We want to solve for r of t. Okay, here it's in r squared, so we're gonna basically just kind of isolate that, right? So we'll make this substitution. We know that r prime from this relationship is lambda over k, so we will take this equation that we have, right, integrate it so that we can find r, and that's going to give me lambda k of t plus the constant of proportionality, right? Since the initial value is r naught, we're going to say that c is r naught, because if I plug 0 into this equation, everything falls out and I'm left with c equals r naught. Remember, this is an equation for r, right? So if I plug in 0 to my equation for r to get out r naught, I end up with the relationship that c equals r naught, right? So my equation for r of t is lambda over k times t plus r naught, right? So again, k is that constant proportionality. Lambda here is that k times r prime, and I have r naught. So here r naught is prime, or I'm sorry, is a constant, which would make sense because r of t is a first order equation. So if I take its derivative, lambda over k is that constant value, right? Which I said over here. So B, if the positive direction is downward, okay, we want to construct a mathematical model for the velocity v of the following raindrop at time t. So here we're going to ignore air resistance, right? So hint, when the mass m of an object is changing with time, Newton's second law becomes F is the derivative of mv, right? Mass times the velocity. So where F is the net force acting on the body and mv is its momentum, right? The mass times the velocity, that's the momentum equation. So the positive direction is now downwards, okay? We want to construct a mathematical model for velocity v, right, of the following raindrop at time t. So let's look at the equations that we have, okay? So we don't have anything here with velocity, right? But we do know that m is kv, right? So we're going to use this equation here, right? kv is this thing, right? Now we're talking about falling, so we're going to have some acceleration here. So I will, sorry, this is volume. So we'll have to do some, we'll have to differentiate mv, right? So mass times volume, its derivative, or its momentum, sorry, this is not volume, this is velocity. So mass times the velocity will give me mass times the acceleration due to gravity. Mass should be a constant here, right? Or we're assuming it's a constant. So when I take the derivative of v, I'm going to get gravity, right? And since the first derivative of velocity is gravity, right? So if we're assuming here that mass is not constant, then we would be using the product rule here, right? It's actually not, because we know that mass here, in this case, is relative to the radius at some time, right? Or the volume, I should say, right? It's a constant multiple of the volume. So here for m, we have, it is going to change over time because the mass is not constant, right? As it falls, it's changing. It's, oops, here we go. It is evaporating, right? So I'm going to have to use the product rule here, right? If it was constant, I would have mg, mass times gravity at this point. So that's one relationship that we can have, right? And then here, since I know it's not constant, we're going to use the product rule. So I get mv prime plus vm prime, and that should be equal to mass times gravity, right? The mass of a falling object. So for m, I'm going to plug in my mass, right, times v prime, which we know is gravity, right? And I'm going to have v times my m prime, right? Or my surface area times that constant proportionality, which is why we have the lambda here. And that's going to have to equal my mass, again, times gravity, right? So we're just using the values we had from the last section and we're plugging them in. You just have to realize that the v here is velocity, whereas the v in the last one is volume. So I probably could have done a better job and used a capital V here instead, right? So apologies for that. Okay. So if we solve for this, right, if we basically try to solve for v prime, so all of this stuff is semi-constants, right? R is a function of t though. If I take all this and I divide everything by k 4 over 3 pi r cubed, this is what I'll get out. So v will be by itself. Here, this and this is the same, so I'm left with g. And then when I divide this by this, this is the constant I get out, right? I get lambda over k, right? 4 divided by 4/3, the 4's cancel and the 3 comes to the top. And then I still have my v that's here, right? Or another way of writing this is if I replace r with its actual function, then this is what I would get out. Okay, so k times r would reduce down to this, and that would be our answer. Either one of these would be okay. Obviously, this is a little more compact, but you can write it explicitly in terms of the function r if you want to as well.